Welcome to the 2021 Holiday Science Lecture. My name is Howard Stone, and I'm pleased to welcome you to this year's event and tell you a little about our theme, which is Let It Flow, a festival about fluids. I hope everyone is well, and I want to begin by just letting you know that this event will take about 1 hour. Closed captioning is available. American Sign Language interpreters are available, and everyone is muted, but we'd be thrilled if you put comments and questions in the Q&A, and at 5 or 6 times during today's event, you'll be asked to answer some poll questions to help us out. Please have fun. We hope you learn something. We hope everyone sees something they might have never seen before, and let's enjoy some scientific themes. This event today is a team effort of many people from Harvard and Princeton. And so we have many people to thank, and you'll be seeing most of them during today's event. We received responses from pretty much everywhere. You see stars in countries from around the globe. And in fact, your people are listening, as far as we know, from all over the world. And so we wish you all a happy holiday season. Now, where to begin? So one of our goals today is to convince you that the world is an amazing place. We want to show you some ideas you might have seen and many ideas you may never have seen and never have thought about. We want to give you a viewpoint about how scientists think about the world. And although it's virtual, we're going to use demonstrations and videos and illustrations to help you think about the themes of fluids and flows. And there's no better place to start than with a quote from Albert Einstein. I'm sure many of the people, if not everyone on the call, has heard of Albert Einstein. And he said, "In the matter of science, the first lesson should contain nothing but what is experimental and interesting to see." Now, he also enjoyed having fun. Here he is having fun. And he also enjoyed some of the foods of the holidays, as shown here, having a little ice cream. So with that, I'll say, we asked you when you registered to tell us a little about what you thought about when you heard the words fluids and flows. And we made a little word cloud that you can see on the screen of many, many words. And some you're going to see, actually many you might see during this lecture. So you can look for your favorite word there. Now, some of you also sent pictures of yourselves or your families or whatever. And so here are a few of the pictures we received, and including one video playing in the lower left. And you'll see on the pictures you see many of the themes that you might also see in today's lecture. Now, we tried to anticipate some of the things that you might tell us on this word cloud. So what we made a little slide with some of the ideas we thought about. And so you could think about the melted wax in a candle. That will turn out to be a fluid. You can think about the smoke from a chimney on a cold day. You can think about many different food-related activities, whether it's the flowing chocolate in a fountain, or gravy pouring over mashed potatoes, or syrup spreading on pancakes. You can think about energy that you need to run the lights in your house, as illustrated in the upper right by a big windmill. Or you might be taking a plane to go visit relatives. I've illustrated already the dog drooling, but you could think about things like swimming, whether it's you swimming or a fish swimming. That involves movements in a fluid, in this case, water. And finally, you can think about the weather, as illustrated by the globe, or if you're a surfer, you can think about the big waves and surfing. As we'll see, all of these activities involve fluids and flows. Now, our first question for anyone in the audience, so we're going to ask you to answer a poll, is you can think about the human body, and we're now going to give you a poll for which of these fluids are in the human body. Please check what you think the answer is, and then we'll tell everyone on the call what the community thought about the possible fluids in the human body. And Sarah will let us know when there's a little time left just so each family can try to have a chance to respond.
Okay, we're going to give it just a few more seconds here.
And we hope everyone's participating.
And here we go. We'll see some results.
Let's see the poll. Okay, so everyone indicated blood. Saliva is in your mouth. It's actually used for testing for viruses. A couple people said orange juice. Well, I guess you drink orange juice. It's not naturally in your body, but you could drink it. Water makes up everything about us. And we breathe air in and out. So you guys did really, really well. So there are quite a number of fluids in the human body as listed here. We included, we thought about sweat and tears and urine, all in addition to blood and saliva. And here's a little video that illustrates some of the fluid motions associated with the body, like blood, sweat, and tears. Or here is a video of animation illustrating blood flow in the heart. And it also illustrates how the fluid moves by using arrows to illustrate the direction of the blood flow. This is from a research group. Okay, excellent. So now fluids, if you think about air as a fluid or water as a fluid, they occur on many length scales, on many distance scales. And I've sketched here the Earth, beautiful picture of the Earth. Now, inside the Earth, you might be aware that inside our planet is our movements of the fluid, and the movements are give rise to earthquakes when some of them happens. And some of you might have studied that in your classes. But if you look now at the picture of planet Earth, you can see several different fluids. And in the atmosphere, as indicated by the white clouds, we also have winds. You see the blue oceans that cover most of the Earth. And if a hurricane happened, you might get an indication of that looking at a weather-like map. And one thing we're going to point out is there are many swirling-like motions, and some of them are illustrated in this nice video that illustrates the kind of motions that occur in the oceans of the world. Showing up on this video is North America. You can see the Florida Peninsula and the motions that occur up and down the coast. The video will go now towards South America and then rotate eastward towards Europe and Africa. And again, everywhere you see the fluid motions here indicated, you see these swirling like flows. Okay, now to give you an indication that fluid motions are extremely diverse and happen in all kinds of activities, I want you to watch this shorebird. It's called a phalarope. It lives in shallow water. And when it gets hungry, it spins in circles. And you could ask why. And it turns out it spins in circles because that helps it get food off the bottom, and then it just has to peck on the surface. And we could tell you more after the lecture if anyone wanted to talk with us. Now, there are fluid-like activities in many places. And here is an image from the sky looking down at the highways of Los Angeles when they're free of a traffic jam. And you see the motion of the cars in two directions. You would call this a flow of cars. You see the white lights coming towards you. You see the red lights going away from you. And it looks like a flow that you might actually see of blood in an artery, for example. Finally, there are two news events I want to share with you from 2021. Some of you might have heard that NASA achieved the first flight of a vehicle on another planet other than Earth. They had a flyer, which you can see in the upper right, a helicopter. It's about 15 centimeters in size, so about 2 hand widths in size. And the helicopter was able to take off and fly a short distance. This was the first flight on another planet. And finally, you might have also heard that last year there were problems with shipping. Shown in the upper right is a video of the path of a ship. It got stuck in the Suez Canal. The ship is the size of 4 football fields, shown on the upper left. And in the middle, it got tilted sideways and blocked the entire canal. A big whoops for the shipping industry. Finally, now I want to turn it over to Janine Nunes, and she's going to start to tell us a little about the science of the fluids that give rise to flows. Janine, over to you.
Thank you, Howard. So hello, everyone. And so we're going to be thinking of phases of matter. And so I want you to answer this question just in your head. What are the three phases of materials, or the three states of matter? You may have heard it that way. So hopefully you came up with solids, liquids, and gases. And we see these all around us. And what I want us to do is think about water, which can exist in three states: solid, ice, as you see here. In my kitchen, I put a block of ice in a pan, and you see the ice is solid and it doesn't spread out. And we have to think about the molecules of water inside the ice. So all matter is composed of atoms and molecules. And the molecules of water can jiggle around a little bit, as you see in the cartoon, but they don't move very much. And so then what I did is I turned on the heat, and I'm heating my pan. And so the ice is going to start to melt. I'm increasing the temperature. And you see the water starts to flow, but the water doesn't have the same shape as the solid ice. It spreads across the bottom of the container. And what I'm going to do is shake the pan, and you see the water is moving and deforming in the pan. And again, let's think about molecules. So what the molecules of water are doing, you see they have more energy and they're moving around a lot more compared to the ice. And they're also spread out more at the bottom of the container. Now, when you heat, you're also, in addition to producing liquid water, you're also producing water as a gas, water vapor. We don't really see it, but the molecules of water in the gas state, oh, they're spread out so much more, and they have so much more energy. And you see that they're spinning and bouncing into each other. And so what's important to remember is that the molecules of water in both the liquid and in the gas, they have a lot of energy and they move more compared to the solid. And so, you know, thinking about gases is a little bit tough because we can't see them. So I'm going to do another example here in the lab. And so I just poured some liquid water into a bottle. So you can pour the liquid. You couldn't pour a block of solid ice. And I'm going to cover the bottle with a balloon, and I've stuck it into the bottle, as you see there. And I'm putting it on a hot plate so I can heat it up. And so remember from in my kitchen, when you heat water, you produce the gas, water vapor. And the vapor, the molecules want to spread out so much more, and they push the balloon out of the bottle and start to fill into the balloon. And so remember, if the balloon wasn't there, the molecules would just escape. And so there you go, folks. I am blowing a balloon with water vapor. And so to quote Santa Claus, ho, 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 and I'll turn it back to you, Howard.
Thank you, Janine. Okay, so the other thing we need to then tell you about are what we'll call properties of fluids. All materials have properties. They allow you to distinguish one object from another, one material from another. For example, a material could be rough or smooth. It could be hard or soft. Well, with fluids, we need to introduce you now to three properties, and we're going to have some scientists and engineers now tell you about density, viscosity, and surface tension. And we're going to do this by learning about their properties by watching some demonstrations. And to tell you about density, I'm going to turn it over to Catherine Holler.
Hi, everyone. I do a lot of cooking in the kitchen, and the scientists that I'm working with on these projects also do that. But one thing we're interested in is density. And you see in the picture here that sometimes when you're trying to mix things in the kitchen, some things like to float on top, and some things go down to the bottom. And that's because they're of different densities. And the definition of that scientifically is how much mass per volume. And like I said, oil and water is an example. If you're trying to make salad dressing, that oil just keeps popping up to the top and the water keeps going down to the bottom. And here to explain some of those concepts of density are two young scientists that I know, and they're coming from the Galaxy Lab.
Okay, and you might have to turn your volume up on your computer. Here we go.
Hello, this is Professor H and Professor J's Galaxy Galaxy Lab.
Today's science is density.
Experiment 1, chocolate milk.
What's more dense, chocolate syrup or milk? Wait, what is density?
It's mass divided by volume, or how heavy something is compared to its size.
Equal amounts of milk and chocolate syrup.
Yum! Which weighs more?
It looks like the chocolate syrup is more dense than the milk.
Brilliant, Professor J.
Cheers to another great discovery.
So that's an experiment you can actually drink, but let's do a little more work.
Oh no,
Experiment 2,
What's more dense,
food coloring
water
or shaving cream?
It looks like the food coloring is more dense than the water and more dense than the shaving cream.
Epic discovery.
So we invite you guys to try these experiments at home. You can try different liquids that you have, and maybe you can join our two scientists, Professor H and Professor J, at their Galaxy Lab.
Thank you, Catherine. So you were just introduced to density, and some of you may have at home a type of thermometer that's shown here on the right. It has the name Galileo's thermometer, though it's not clear Galileo quite knew it in this form. And this thermometer works by using the density of the different objects in the liquid. And therefore, as the room changes temperature, different of these spherical objects rise up and down, and you can read the temperature from a marking on the little spherical objects. So this keeps track for you of the room's temperature, but it uses the property of density, the sinking or rising of objects, to do that. And finally, you're not aware of it, but we all change the temperature of the air around us. And if you have the right way to look at the air, or to so-called image the air, you can see the flows in the air that are caused by the fact that you heat up the air around you. And here you can see that the woman breathes out her nose, there's air rising across her body, and when she breathes out, you can also see the air coming out of her mouth. So here are cases where you can actually visualize the airflow in the room, in the world around you. Okay, the second property we want to tell you about is viscosity, and to do that, I'm going to turn it over to Nikki Abbasi.
Thank you, Howard. Hi, everyone. My name is Nikki, and I'm excited to tell you more about viscosity. Viscosity is a fluid property that describes how thick or runny a fluid is. The water that you drink every day to stay hydrated, the hot chocolate that you make on a cold day, and the maple syrup that you pour over your waffles or pancakes, they all have different viscosities. And the viscosity highly depends on the molecular structure of these fluids. Some may be really, really viscous, and some may be less viscous. For example, maple syrup is much more viscous compared to water. Now, let's better understand what viscosity is. So far, we have learned that both gases and liquids are fluids, and they both have different viscosities. But in order to better understand what viscosity is, let's think about a deck of cards. So imagine you have a deck of cards, and there's nothing in between the cards in the deck. And what you're trying to do is to slide the deck against all the cards. So what's going to happen is, if there's nothing in between the cards, it's relatively easy to slide the cards, or in other words, shear the cards against each other. And that is analogous to a fluid that has low viscosity, say water. Now, imagine another case. You again have the same deck of cards, but you're going to add glue in between the cards in the deck. And what you're going to do, again, is going to shear or slide the cards against each other. You'll see that it's much, much, much harder to shear or slide the cards when there's glue in between. And that is analogous to a fluid that is highly viscous, say, again, maple syrup. And you experience this in the kitchen every day when you're trying to use a knife to spread, let's say, honey on toast or ketchup on hamburger, or while even you're painting on a canvas. You're essentially experiencing how easy or difficult it is to spread these different types of fluids on the substrate. All right, so far we have learned about what viscosity is. So we're going to do an experiment. So we have a glass of water, a glass of honey, and 2 different spheres. And we're going to drop each of these spheres in water and honey. The question I have for you is, in which liquid, water or honey, does the sphere fall faster? Let's take a moment and answer the poll. So the choices are water, honey, you think they fall at the same speed, or you're not sure. All right. Let's see if everyone can answer. All right, it seems we're going to get the results in a bit. All right, so most of you, 88% said that water, in water, the sphere is going to fall faster. Well, let's do the experiment to see. So if we do the experiment, you'll definitely see that in water, sphere falls much, much, much faster. And that has to do with the fact that water is less viscous, so it's much easier for the sphere to travel through the column of water compared to the column of honey. All right, so let's think about another thing. What's going to happen if we increase the temperature of a liquid? What's going to happen to its viscosity? If you increase the temperature, you're giving more energy to the molecules. So it's much, much, much easier for the liquid molecules to slide against each other. Therefore, you're effectively reducing the viscosity of the liquid as you increase the temperature. And you saw that in the hotter honey, it was much easier for the sphere to fall rather than the cold honey. All right, so now we know what's the effect of temperature on viscosity. Now, there are some fluids that at times it can act a little bit weird and strange. There's an example for you, cornstarch mixture in the kitchen. So if you were to mix cornstarch with water, you'll see how runny and flowy it is. It's like a liquid. Now, I've got a question for you. Let's say you're gonna make the cornstarch mixture in the kitchen, and now you're gonna take a hammer and try to beat the cornstarch mixture. What do you think is going to happen? Does it splash all over the place? Does it make a dent? Does the hammer break? The cornstarch mixture breaks? Or you think nothing happens, you're not sure? Let's take a moment and see what you think. All right, hopefully everyone is thinking about this.
We'll see what the poll says.
All right, it's coming. Oh, okay. So 31% say it splashes, 36% say it makes a dent, and the other answer. So again, let's see a demo and see what happens. So again, we have the cornstarch mixture, and we're gonna hit it with a hammer. It doesn't splash. We thought that it's a liquid, but when we try to beat it with a hammer, it doesn't splash. Why is that happening? Because in the really, really small time that you're trying to beat the mixture with a hammer, the molecules do not have enough time to move around. So that's why a liquid, the cornstarch liquid, can sometimes act solid-like in really, really short times. And you can make use of this behavior of cornstarch mixture and fill swimming pools with cornstarch mixture. And if you're interested, you can run around and do all types of different acrobatics, and you're not going to sink in as long as you're active. But the moment that you stop moving, you're going to sink in. There's another example of such weird liquids, and that is silly putty, which you may have played with. So if you take a sphere of silly putty and bounce it against a wall or a table, you'll see that it bounces back. It doesn't splash or anything. But if you take the exact same silly putty sphere and let it be on a surface over a really, really, really long time, it would spread. And that is because the fact that at really, really long times, silly putty flows, it's fluid-like. Whereas in really, really short times, it acts solid-like. And here on the right-hand side, we shaped silly putty in the form of a scarf for this polar bear, Professor Polar Bear, our mascot. And we can see that at really, really long times, the scarf is actually going to flow. And at some point, it makes actually a sweater for our Professor Polar Bear. Back to you, Howard.
Thank you, Nikki, including showing how a scarf becomes a sweater. Okay, the last property we want to tell you a little about and make a number of new connections for you is surface tension. And to tell you about that, I'm going to turn it over to Paul Canilo and Ambika Somasundar.
Thank you, Howard. All right, so now that you know about viscosity, I'm going to tell you about another fascinating property of fluids called surface tension. So let's just look at some pictures and try to understand what surface tension is for ourselves. So if you look at the top left picture, it's a picture of an insect called water striders, basically standing on top of a surface of water, say on the surface of a pond or something. And that's really fascinating. And if we look at the video on the bottom left, what we see is that the same insect, but this time walking and jumping around on the surface of water again. Now, I don't know about you, the last time I tried to stand on top of the surface of water, it didn't go well for me. So what's happening here? How are they able to stand and walk on top of water? So what's happening is very analogous to what happens when we stand on top of the surface of a trampoline. So we know that the surface of the trampoline is connected to the edge of the trampoline on all sides, and it's pulling the surface of the trampoline from all sides. So we say that that surface is under tension. And that is what allows for us to stand on top of it and even jump on top of the trampoline. So the same thing is happening with the surface of the water. So the surface of the water is being pulled from all sides. So it's under tension, and that allows for things that are light enough to stand and even jump on top of that surface. Okay, let's go into the lab and look at a video and try to understand a little more about surface tension. So the question that I want to ask is, do paper clips sink in water? Everyone can take a minute to think about it. I'll show you the image of a setup that we have. So we just have a container with water in it, and then of course air above it, and then light behind it to illuminate the experiment. So you can already answer the question of whether the paper clip will sink if you look carefully. So here we're bringing a paper clip and we let it go, and it in fact sinks to the bottom as you would expect. But does it always sink? Would surface tension be strong enough to make the paperclip stay on top of the surface? So let's watch this. So what you see is that if we place the paperclip carefully on top of the surface, it in fact, the surface tension of water is strong enough to keep it above the surface of water. So it's not a magic. If we push on it hard enough, it will fall into the surface. Okay, now we can ask the question, what happens if we put multiple paperclips next to each other? So think of putting multiple bowling balls or something next to each other on your trampoline. Would they stay where they are? Would they come together? Would they move apart? So here we're putting multiple paper clips next to each other. And what you're in fact seeing is that they actually come together, right? Just as two bowling balls would come together on the surface of the trampoline, because they kind of make a dip on the surface, and then because of that, it comes together. So here, what we just did was add a little bit of soap to the water, and we saw that it immediately caused the paper clips to sink to the bottom, and now we're not able to put or float any paper clips on top of that surface. So what happened? So putting the soap on the water basically changed the surface tension. So we can say it lowered the surface tension, so it made the paper clips fall through the surface. Okay, so this idea of things coming together on the top of surface of liquid is something that you guys have probably noticed even today, this morning, when you sat down for breakfast. So it's the reason why your Cheerios, the cereal, clumped together on top of a bowl of milk. And it's also the reason why you see bubbles clumped together on top of your cup of hot cocoa or chocolate milk. So I hope the next time you sit down for breakfast, you think about surface tension, and then you'll never be able to look at breakfast the same way. So now Ambika is going to talk a little bit more about surface tension.
Thank you, Paul. Hi, everyone. Okay, so now Paul has shown us what happens on the liquid when your cup is filled with water or milk or your delicious holiday drink. Now, here is a question for you. What do you think will happen when you finish your cup of holiday drink and you're trying to get to the last bit left at the bottom? How does the water appear on your almost empty cup? Here are the options that you have, A, B, C, and D. So maybe we can take a few moments to answer this question. So which one can it be?
We'll give just a few more seconds here.
Hopefully everyone can participate. That'd be great.
Okay, great. So now we have the answers here. So all of you have at least one right answer because it can actually be any of these three options based on the material of the cup. So in order to find out how these water would appear, we did an experiment in the lab where we looked at water droplets on three common materials that you find in your house. So these are plastic, glass, and metal, such as aluminum foil. So here we can see that the water stays like a drop on the plastic, spreads out on the glass, and spreads out even more on the aluminum foil. So what this means is that the aluminum foil actually likes the water and it spreads out on it, but it does not like the plastic surface and it wants to stay away from it, just stay as a drop. So this happens because the surface tension between water and aluminum foil is different than the surface tension between water and plastic. Okay, so now let us do an experiment together called the drops on a penny experiment to see another cool feature of surface tension. So for this experiment, you will need a penny, a medicine or an eyedropper, and a cup of water. So what we will do is we will first place this penny on a clean and flat surface. We will slowly add drops of water onto the penny and see how much water the penny can hold. So remember, while you're doing the experiment, make sure to keep count of how many drops you're able to add until the water runs over the edge. But before we do the experiment in the lab, let's take a guess of how many drops of water the penny can actually hold through this polling question. Okay, so as you're trying to answer this question, we will continue the experiment and then we'll see how many drops it can hold. So as we continue the experiment on the next slide, you can see that the penny is able to hold many drops of water. So you can keep adding more and more and more water, and you can still see that the water is still on the penny. And in fact,
we can, Ambika, maybe we can see what the poll answer was.
Okay, sure. Okay, great. So it looks like almost everyone has answered all different kinds of questions. So we'll find out in this experiment what happens. So as you add more and more, the water forms a dome-like shape. And this is because the water droplets are clinging to each other because of surface tension. And finally, when the surface tension can't hold the water anymore, the water falls from the penny. So in our experiment in the lab, we saw that the penny is able to hold 26 drops of water. Now, of course, this number will also depend on a lot of factors like your dropper size or how clean or dirty your penny is. And in fact, if you change the liquid from plain water to salty water or even oil, you will observe that the number of drops that the penny can hold will be different. And this is because different fluids have different surface tensions. All right, back to you now, Howard.
Thank you, Ambika, for this great demonstration and experiment. So we've shown you a number of different things about fluids. And now I want to tell you just briefly about the idea of swimming, which you're familiar with. So if you've been to an aquarium or seen on TV, you know they're very large whales. They can be up to 30 meters long. That's about 20 times bigger, longer than we are. But of course, there are smaller fish that are sort of the size of your hand or smaller that have many different fins that you can think about what their purpose is. And these animals are swimmers. But here's an amazing, and you can also see that when fish swim collectively, when they're a population like we are, they can also form fascinating patterns. But I now want to play a video of what's called an archer fish. The archer fish lives underwater, but it's capable of shooting a jet of water up to leaves over the surface to hit insects that might be on the leaves. It's very accurate. And here it's hitting the leaf and getting an insect to fall into the water and eat. So if you think about different features, here's a fish that's learned how to shoot an arrow of water. Now, these are fish that are sort of the size of that we are. I'm now going to turn it over to Bonnie Bassler, who's a professor of molecular biology, who's going to tell us about very small swimmers. Bonnie, over to you.
Okay. All right. Thanks. Hello, everybody. Happy holidays. I'm glad to get a time to talk to you. So everybody's familiar with the fish and the animals that Howard was telling you about and how they navigate through water and get from here to there. And so what I want to tell you about are the smallest swimmers in the world, and those are the bacteria. And so bacteria are ancient organisms. They're the most ancient organisms in the world, and they're really, really small. So this is a picture of what a typical bacterium looks like, and they live in a fluid world. So they live in liquid. And you can't see them. You need a microscope to see them. And so just to try to understand how small they are, you would have to put 100 bacteria end to end to end to end to get the width of a single human hair, right? So they're really tiny. And so you would think, well, that's a terrible fate. You know, they'll just get tossed around in the liquid in the water and they'll just go willy-nilly. Like, so how can they swim? So it turns out that bacteria or evolution solves that problem, and they can get from here to there. They're not just victims. It turns out, and Howard's going to show you a video that's taken under a microscope so that we can see the bacteria. And what you can see is that they're shooting through the liquid, right? And they are going from here to there in directions. And if you watch carefully, Howard will show it to you again. They kind of swim straight, and then they change directions and shoot off in another going a different way. And the way the bacteria do that is because they have a motor, they have gasoline, and they actually have a propeller. Like on a boat, they actually have a propeller, and this motor and propeller shoots them through the liquid, and they also have a steering wheel, which lets them change direction. So if Howard goes to the next slide, we're going to look at a cartoon depiction of these bacteria. And so what they have, the bacterium is the oval, and what they have are all these rope-like projections that hang off sort of their rear end, and that's shown on the left slide. And those ropes will bundle around each other like a braid, right? And when those bundle around, they turn like a propeller on a boat, and the bacteria shoot straight through the liquid. So that, right, and they have a direction. But then when the bacteria needs to change which directions it's going, those ropes will uncurl, and that's shown on the right, and the bacterium will tumble around and randomly end up in another direction. The ropes will wind around each other, make the propeller again, and off the bacteria go. So they run, they tumble, they run, and they tumble. And so these rope-like projections are actually connected to one of the world's smallest motors. And so scientists have figured out what that motor looks like. It's made from about 50 or 60 biological proteins. So biocomponents make the motor, and that's shown on the right-hand side. So at the sort of very end of the bacterium, is this motor, which is the bottom part of the right-hand slide. And then those hair-like or those rope-like projections stick out of the motor, and the whole motor turns, the hairs bundle up, a rotor forms like a boat propeller, and that gives the bacterium the ability to swim in a particular direction through liquid. So it is not just tossed around randomly. And we actually know we're right. I mean, the scientists, we know, oh, you can watch it again. Sorry, you watch it again. And so now you're going to see, when you see the braid, right, the bacteria go in one direction, then they tumble around, you see it all fly apart, the little rope, the individual ropes fly apart, and the bacteria tumble. They reorient their direction, the braid forms again, and off they scoot. And scientists actually know that we're right about how that motor works. Remember, you can't see it. It's invisible. So how would scientists figure that out? So they actually did a really cunning trick to originally figure out that that machine turns like a boat propeller. What they did was they glued the ropes to the surface. So if they glue the ropes down, now that rotor, that propeller can't turn. And so what happened, and that's shown on this video, is the bacterium turned. So if you hold the ropes so they can't spin, what you can see right in the middle is that the bacteria turns around. And so there it goes. And so that was the proof that that was a motor, and that the motor spins with a propeller just like on a boat. So that's how the evolution has solved. If you go to the next one, Howard, how evolution has solved these bacteria swimming through liquid and getting where they want to go, and not being subject to just tossing and turning. And so that's up on the left-hand slide. But it turns out there's many, many different kinds of bacteria, and they have solved this problem in different ways. Some of them do what's called swarming. So they actually crawl like spiders and they stick on the surface. Others are like corkscrews, and the whole bacterium spins as it goes through the liquid. And then finally on the bottom slide, sometimes they team up and they use pushing against one another so that they all move along sort of like a freight train. But they all live in liquid environments and had to figure out these biological solutions to allow them to have movement and direction. And so I hope you like these small machines, and I'll turn it back over to Howard for the next interesting thing that you can learn. Thank you.
Thank you, Bonnie. So we're now going to turn to a slightly different theme and tell you a little bit more about flow. And we're going to start with the concept of pressure. And Camille Duprat, a visiting professor from Paris, is going to tell us about that. Camille, over to you.
Hi, thank you, Howard. So I want to talk about pressure. So imagine you're pushing on an object. Here's this little filing cabinet, which is on wheel. So you can, when you're pushing, you're applying a force, and you can even move the cabinet. But if a friend is, say, pushing on the other side with the same force or the same strength, then the cabinet is not moving. Well, in fluids, we've seen that there are molecules which are moving around all the time, bouncing off the surface of things, and they're actually pushing all the time on all the surfaces. And in fluids, we call this push pressure. So in the air, we don't see objects moving around all around us. That's because the air is pushing all the time on all the directions, like these two scientists here. Indeed, air is all around us. And on Earth, it's in a box that we call the atmosphere. And in the atmosphere, the air is always pushing against all the surfaces. There is a pressure that we call the atmospheric pressure. So to learn a little bit more about pressure and how it is related to flow, let's start with an experiment. So for this experiment, you're going to take two sheets of paper, and we're going to blow in between them. But first, let's answer a small poll. What do you think will happen? When I blow between the sheet of paper, will it just stay the same? Will they move further apart as I blow? Will they come closer together? Or maybe you're not sure. So let's see what the poll says. And you can prepare two sheets of paper. So everyone has some time to think about it. You can even start the experiments if you've already done answering the question to see if your imagination was the right answer. Do we have the results of the poll? I'm preparing then for my experiments. Okay, so a lot of you thought that the sheets were going to move further apart, and some that they will move together, and some that nothing much will happen. Well, let's try to do the experiment then. So if I take the two sheets and I'm now trying to keep them straight and then blow, well, you actually see that they are coming together. So what happens? Well, I told you that the pressure of the atmospheric pressure is always pushing all the time on all directions. So it's pushing on the both sides of the sheet, doesn't move. But what happens if one stops to push? Well, as you can see here, if one person stops pushing, well, the cabinet just moved. And like these two scientists just experienced. So what we did is exactly the same thing. As we blow in between the sheets, we stopped pushing or we pushed less in the center. That means that actually we decreased the pressure. So as we blow, we decrease the pressure, we push less inside and outside, and everything is coming together. So we see here that the pressure and the flow are related. Indeed, if we have a low velocity or a low speed, scientists we like to call speed velocity. If we have a low speed, we have a high pressure and the sheets are just staying straight. Now, if I increase the speed, I have a high speed, I have a lower pressure and the sheets actually come together. And so there is this link between pressure and speed that we scientists like to express with algebra. So some of you have seen algebra before. If you haven't, or even if you had, don't be scared, but I'm going to show you an equation. And this equation actually just tells you that if you add the pressure that we call with the letter P here, and something that contains the density that we've heard about, and the speed or the velocity, well, this adds up to a constant, and that's a Bernoulli equation. What that means is that if I increase the velocity, I have to decrease the pressure. Or on the contrary, if I decrease the velocity, I have to increase the pressure. So we have this link between pressure and speed. But this has many effects around us. And to see that, let's first look at our colleagues in Harvard that made an experiment that show you what Bernoulli can do.
So, welcome to Lecture Hall B. We miss you, but we've got some demonstrations to do, and we're going to do them by video. I have here a simple bendy straw and a ping pong ball, and we're going to look at the Bernoulli effect. So the first thing I'm going to do is I'm going to hold that vertical and see what happens when I blow through this straw. So it looks like I'm blowing and the ping pong ball is sitting on a column of air. But is there something more going on? Let's put the nozzle at an angle and see what happens then. So you can see that the ping pong ball is actually hanging over nothing. It's held in the column of air. And we're going to move to a slightly larger scale to investigate that.
So this is Daniel Rosenberg, and he's now going to do yet another demonstration with a bigger ball here.
Okay, so we're going to do the same demonstration again, except instead of a straw, I've got a leaf blower, and instead of a ping pong ball, I've got a beach ball. And I'm going to follow the same procedure. First, I balance it up on top of a column of air, and then I tilt the airflow and see what happens. So. And that's the Bernoulli effect.
Thank you, Daniel.
Thank you, Daniel.
That is the Bernoulli effect, and Camille's going to tell us a little bit more about it now.
Yes, that was an amazing experiment. So why did the ball, or how did the ball fly? Well, as we blow, we made this very high speed flow of air. but when it touches the ball, it has to slow down. And so this creates this high pressure that's able to carry the weight of the ball. At the same time, we have a lot of differences in speeds everywhere, and the ball is trapped in a jet of air due to the differences of pressure. And then we can tilt the air jet, and the ball will just stay in the air jet. And this effect is also something that actually allows plane to fly. So if we look at an aircraft which is flying, well, the air has to go around the wing. So if we take a cut of the wing, so that will be shown by this little sketch here, we have this very specific shape, and we can look at the flow around the shape of the aircraft. And this is an experiment that our colleagues at the University of Cambridge did. And what they did is that they added smoke to the air so we can see the air going around the wing. And if you look closely, and it's going to play again, what you can see is that the air actually goes faster on top of the wing and goes slower below the wind. So we now have a high velocity, high speed flow on top of the wing, so a lower pressure, and we have a slower flow, and so a higher pressure on the lower side of the wing. And so there's a difference of pressure, and this difference of pressure actually generates a force that engineers called a lift force, because it's a force that lifts the plane in the air and allows it to fly. So we see here that with difference of speeds and difference of pressure, we can lift things like aircrafts, but we can lift many different things. And we've done an experiment in the lab where we took a glass filled with liquids and we put a straw in it. And we want the liquid to go up the straw. And to do that, we're actually going to blow on top of the straw. So we're creating a jet of air. And you see that the liquid rises up the straw and is blown away at the tip of the straw. So again, we have the same thing here. We're blowing, and so we're doing a fast flow, which has a lower pressure that actually drives the liquid from the high pressure in the glass to the low pressure on top of the straw. And we can actually empty the liquid. So think about a chimney in your house. The tip of the chimney is high up in the wind, and the wind actually helps creating a draft that takes the air from inside to outside. So we use the Bernoulli effect to build chimneys, for example, but we're not the first one to do it. And animals have been using this effect for a long time. So take this little guy, for example, that is a prairie dog. They live in prairies, and they actually build their home underground in what is called burrows. And these burrows contain tunnels and different rooms and look very cozy. But one of the problems they have is how to ventilate those spaces. They cannot use air conditioning, but the good thing is that they know about the Bernoulli effect. So what they do is actually they build these little hills of soil at one of the entrance of the burrows. And so there is a difference of height between one entrance and the other. As the wind blows above this little hill, it accelerates like we've seen with the wind. And so we again have a slower flow with a high pressure and a faster flow with a lower pressure. And again, this will drive the fresh air to go through the tunnel and ventilate the space. So now the prairie dog can gather his family and friends in a very safe, well-ventilated home. There are different other animals that use Bernoulli to ventilate their homes, but also to play sports. So for example, soccer player use the Bernoulli effect to create these very dramatic kicks where the ball can actually fly around the defenders for an unstoppable goal. So you can now try to think about how this is related to the Bernoulli effect, and we can talk more about it after the lecture, but now back to you, Howard.
Thank you, Camille. So at this point now we're going to change to our final topic, which is the topic of swirling motions, where we introduce a new term to you called a vortex or vortices. And to tell you about that, I'll turn it over to Professor Petros Koumoutsakos from Harvard. Petros, over to you.
Thank you very much, Howard. Happy holidays, everyone. I just realized that my first name is the Greek translation of Howard's last name. But I'm here to tell you about vortices. And what are vortices? Vortices are everywhere. And whenever you have fluids that are moving around, then what we scientists often say, if there is a difference in the way that the fluid is moving from one place to the other, we say that there must be a vortex there. Now, when we look at the weather, very often we have hurricanes and cyclones and all these things that winter usually brings us. And then here you see how the air is swirling and turning around. And then we use the clouds here to visualize this structure. And this is actually a big vortex. Camille told you about how airplanes fly, and she actually very nicely told you how the air is flying in a different speed on top than the speed that it has on the bottom of the wing. So that means that there is a difference in the speed of air. And because there is this difference in the speed of air, there is a vortex there. And even though you don't see these vortices, we can see how we can actually visualize them later. And finally, one of the reasons that our heart is beating and is beating nicely is because there is a vortex. And how is this vortex being formed? Well, when the blood is going inside this container and then it goes through the valves, then a vortex is generated. And actually, when the blood flow stops, this vortex helps to close the valves. So there's no muscles, but there are vortices which are acting as muscles for the fluid to close the valves. So vortices are wonderful and they have beautiful structure. And even though we cannot always see them, there's people like Leonardo da Vinci, who is more famous, not for vortices, but for painting the Mona Lisa or the Gioconda. And he was actually looking at fluids, and I suggest you do that too. And he was looking how the fluids are swirling, and he was making all these beautiful paintings and sketches of vortices. And this is a beautiful way to get introduced to art, by trying to draw all the swirls that fluids are making. So what is a vortex? As I said, a vortex is something that that rotates the flow, and at the same time, whenever a flow rotates, there is a vortex there. And now the vortices are structure, and these structures are coming in different shapes. One shape can be a cylinder, and then this is a cylinder that is generated behind the aircraft wings. And then there's another structure that we will see later, which is called a vortex ring. So here's the aircraft, and you see the aircraft is flying, and it's flying near a tower. And then in this tower, there is smoke coming out. And you see that the airplane has gone very, very far away. But now that's the time that the air starts to spin. And this is because the vortices from the wings of the airplane are still there. And actually, if you happen to be on an airplane and you're waiting on the tarmac to take off, the reason that very often you wait is because there is a bigger plane that has taken off in front of you. There's vortices behind the aircraft, and you don't want to fly in the vortices of this aircraft because there will be a lot of turbulence. So vortices are behind airplane wings, even though we don't see them, but sometimes through these visualizations, we're able to do so. Now you can make lots of vortices and look at them in your kitchen. So what you can do is you can take a cup of water and put some milk, or a cup of coffee and put some milk, or anything else you want. And then you use a spoon, and then the spoon is disturbing the flow. And as soon as the flow is disturbed, you get all this swirling motion. And very often you have this swirling motion happening in very particular patterns that are very, very beautiful. So people like myself who like to do things in the computer, we do simulations where we take a cylinder and we move it in the fluid, and then we have vortices. The vortices that are blue are spinning clockwise. The vortices are red and yellow. They're spinning counterclockwise. And then these vortices, they keep going even when we stop the cylinder. And you see now these vortices are moving forward in front of the cylinder, and then they make new vortices being generated. And that's actually a way that turbulence is happening, with big vortices making small vortices and so on. So let's look at the other structure, which are vortex rings. And let's hear this from the Royal Institution in London.
Here at the RI recently, we've been having a lot of fun with smoke rings. I built this giant cannon for this year's Christmas lectures, and I thought, why stop at smoke? Smoke rings, fire rings, bubble rings, they are all vortex rings. Vortex rings are formed when a fluid, which can be a liquid or a gas, is forced through a hole. This forces the fluid to curl back in on itself, which creates a distinctive ring shape called a torus. Fluid dynamics can help us understand why the vortex rings form, which is why I've put together this plastic bag DIY cannon, When you fire a smoke ring, you force the smoke from inside the cannon through the relatively still air of the room. To start with, the smoke is basically a fast-moving ball. As it emerges through the opening, the smoke on the outside of the ball is being slowed down because of the friction between it and the edges of the hole. Once it leaves the cannon, there is friction at the interface between the smoke and the air in the room. This means that you get smoke in the centre of the ball moving faster than the smoke around the edges, and so the smoke on the edges starts to curl around and form a mushroom cloud. As the smoke reaches the back of the cloud, it's drawn into the faster moving current of air in the centre. It's this flow pattern that eventually causes the ring to form.
So vortex rings, what are the vortex rings? You can generate them by having a pipe and hitting it hard. You also generate them with your mouth. So every time you blow, you're generating a vortex ring, and then the vortex ring is traveling and is going to the direction in which you're blowing. So here's a contraption that you can use to blow all the candles in your house. You make a box, you open a hole, and when you hit the box, you move the air that is inside the box. A vortex ring is generated. The vortex ring is traveling. You don't see it there, but it is there, and that's actually what eventually goes and extinguishes the candle. So also you can see lots of vortex rings here. Whenever we talk, you see how the person is generating these jets, and what you see are actually cross sections of vortex rings. And that's why it's very nice to wear a mask, so that, or to put, when you sneeze, your mouth to your elbow, because in this way you don't allow the vortex rings that you generate with your mouth to travel and affect other people. Finally, we are not the only ones who can make vortex rings and use them to do things like blow candles. Dolphins, which are very smart animals, they're having a blowhole, and out of their blowhole they can blow air, and when they blow air they generate these beautiful vortex rings, and they are aware that they're making these vortex rings. So these are like making your own toys, and then they go and they cut them and they do beautiful fluid mechanics, much better than any human can do. It's very difficult for any one of us to do this, and I will let you enjoy this video, and I want to wish you happy holidays again.
Thank you, Petros. So I'll just leave you with one final Christmas-inspired demonstration performed by Daniel Rosenberg at Harvard. We took 2 different colored flames by using 2 different molecules, and he puts it on a rotating table, and we're going to create vortices through the flames, and then you get to watch this beautiful pattern form when he rotates the entire container. So here's a little treat for you of 2 vortices with Christmas colors, these 2 intertwined flames. So that brings us towards the end of our program. We've tried to share with you many different ways that you see fluids in the world around us, many different ways that you see flows in the world around us, whether it's nature or weather or breakfast. We've tried to show you that the flows and the movements can be complex, but they can also be beautiful. And you can also understand some of them using the concept of Bernoulli that we introduced and tried to illustrate for you. And finally, I will just say, please, we hope you enjoy a very safe and happy fluid holiday season. With that, I just want to say that the idea for this lecture actually was generated already in the 19th century by Michael Faraday, who worked at the Royal Institution, which was where the vortex ring video was made that we shared with you. Shown in the lower right is a simulation of flow past a Christmas tree performed by Petros Koumoutsakos and his research group. And with that, I want to say remind you this was just a real team effort. You got to meet many of the people. And with that, I want to say happy holidays, or as our dogs say, happy holidays. and wish you a safe and happy holiday season. It's been a pleasure for all of us to share this with you, and many of us can stay online if there's some things you'd like to talk to us afterwards. But now over to you, Catherine. If anyone would like to stay online, we're happy to talk with you. I guess there's some questions